Hi students, I hope you all had a lovely spring break and you're ready to jump into homework 12. Homework 12 extends what we've learned about logarithms and exponentials, and it'll throw some word problems at us and some things like population growth and exponential growth. But before we get to those word problems, we need to talk more deeply about some of the rules that you'll need to use to solve problems that contain logarithms and exponentials. So this first video focuses on our logarithm rules. There are 3 rules that we haven't talked about yet that help us to simplify our problems and solve for variables. So the first rule is an exponent property rule. And here's how this works. If you have a log, let's say log base b, of x to the y power, this power here, this exponent, is allowed to pop out front of your logarithm. That's just a convenient property that we will use a lot. So you could rewrite this as y times log base b of x. So if you have an exponent on the variable inside your logarithm, you can move that out front, and while it's out front, it's multiplied. So that would be y times log base b of x. So of course, equal signs work in both directions. So if you start out with something being multiplied in front of your logarithm, you can move it into the exponent position. So it can go both directions. And we'll use both of these features in examples today. All right, the next rule we need to learn is the multiplication property of logarithms, and that looks like this. If you have a log of 2 things being multiplied together, say x times y, you are allowed to split this up into 2 separate logarithms, log base b of x and log base b of y. When you split it up, however, the 2 logs are being added together. So inside the log, if they're being multiplied, you can split them apart, but then it'll be added. Now, of course, equal signs work in both directions, so if you start out with 2 logs being added, you can combine them into 1 log where they're being multiplied. One thing you do have to be careful of, though, this only works if the bases are the same on both logs. Notice that you have to retain the same base in all of these examples. So for instance, if you had, log base 3 of x plus log base 2 of y, you could not use this rule to combine these into the same log because they have different bases. All right, so finally, the division property rule is a lot like the multiplication property rule. You have, say, log base b of x divided by y. You are allowed to split this into 2 separate logs. And let me let you take a guess here. If your multiplication rule turns into addition, what do you think your division rule turns into? The opposite of addition, subtraction. So these rules, all 3 work in both directions, and we'll use these to either split logs apart, combine logs, or simplify them as we need. So let's actually put some of these into practice. Question 4 is a pretty straightforward example, and this is just practicing with our new rules. So the first question says natural log of 6 plus natural log of 3 equals natural log of z, and they want us to find z. So the way we're going to do that is on the left-hand side, we want to simplify this, so we need to combine this into a single log first. So since these both have the same base, remember natural log just has a base of e. These all have base e. We're allowed to combine these 2 logs together using our multiplication rule. So this becomes the natural log of 6 times 3 equals the natural log of z. And now that we just have a single log on the left and a single log on the right, we can eliminate these logs by doing their inverse. The inverse of a log would be to turn the log into an exponential. And since these are base e, the way we eliminate them is we take e to the power on both sides. So let me maybe write this a little more clearly. What we're doing in this step to eliminate those natural logs is we're taking e to the power of both sides. So let me write this out. We have e to the natural log of 6 times 3 equals e to the natural log of z. E to the natural log cancels, leaving us on the left with just 6 times 3 and leaving us on the right with just z. So I did this problem very step by step, and every little step I wrote out. You can kind of shortcut these, as you can see. Writing this step out is a little unnecessary. For instance, you can kind of just cancel these out at this stage. Or another way to look at it, when you're at this step, if the natural log of this equals the natural log of this, then of course the two things I circled, the 6 times 3 and the z, have to be equal to each other. So hopefully we can kind of use common sense on some of these to figure out next steps without really having to think too hard about these. So you end up with z equals 18. All right, so that was our multiplication property in practice. Now let's look at the next example. We start with natural log of 6 minus natural log of 3, and that's equal to natural log of z. And we want to know what z is equal to. So very similarly, we want to combine these two logs into one, and this time we're going to have to use our division rule. So since these two things are being subtracted, when we combine them together, we end up with natural log of 6 divided by 3 equal to the natural log of z. And we cancel the natural logs out the same way here. We take e to both sides. E and natural log cancel each other out, so you end up with 6/3 equals z, which simplifies to z equals 2. And for the third example, we have 6 times the natural log of 3 equals the natural log of z. Now, we can't, well, we could, but we don't want to take e to both sides right now, because what we'd be taking e to the power of is 6 times natural log of 3. So this doesn't just straight cancel. This side would straight cancel, but the left-hand side would not. So we need to manipulate this a little bit before we take e to both sides, and that's where our exponent rule comes in. When you have something in front of your log, you can pop it into the exponent position of whatever's inside that log. So we're going to rewrite this as natural log of 3 to the 6th power equals natural log of z. And now that we have just a natural log on both sides, you can take e to the power of both sides. The natural logs will cancel, and you end up with just 3 to the 6th equals z. And plug that into your calculator, you end up with z equals 729. Question 7 is asking you to do basically the same thing, but once we get rid of those logs, we're going to have a more complicated job ahead of us. So we start off with the natural log of 2x minus 1 plus the natural log of 6 minus x equals the natural log of 7. Now we can't take e to both sides just yet, because we'd be taking e to this power, and that is just ugly. So what we want to do is we want to take these two logs and combine them into one. And since they're being added, we use our multiplication rule. So this becomes natural log of 2x minus 1 times 6 minus x. Notice it was combined into a single log, but I had to use parentheses there to preserve the two factors. Now that we just have a natural log on one side and a natural log on the other side, we can cancel these by taking e to the power of both sides. Then what we're looking at is 2x minus 1 times 6 minus x on the left and 7 on the right. From here, this is relatively easy to solve. We don't have any natural logs getting in our way. Now we just need to FOIL this out and figure out what x is. So when I FOIL, I get 12x minus 2x squared minus 6 plus x equals 7, which is negative 2x squared plus 13x minus 13 equals 0. And in order to solve for x here, I think we're going to want to use our quadratic formula, so x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So that'll give us negative 13 plus or minus the square root of 169 minus 104 all over negative 4. And that will simplify down to positive 13 over positive 4 plus or minus the square root of 65 over negative 4. But since the plus or minus accounts for this negative here, you can kind of eliminate that negative. So this is our answer. Well, rather, this is our two answers, and you're going to need to put the smaller one in, put the smaller one in as x1 and the larger one in as x2 because they specify they want the smaller one first. And our smaller one is always going to be the minus, and the larger one is the plus. All right, in question 8, we're dealing with the same type of problem, but this one's a little different because we don't have natural log. We have log base 5. So let me explain something really quickly. If I have like the natural log of x equals y, and I want to eliminate the natural log, I take e to both sides because e and natural log are inverses of each other. Because remember, natural log is just log base e. It's a shortcut notation. That's all it is. It's just log base e. So that's why we take e to both sides to cancel this. In the example we're on right now, we don't have a base of e. We have a base of 5. So to eliminate this logarithm, I have to take 5 to the power of both sides. So on the left, 5 to the power of log base 5 are going to cancel. So we end up just with 2/5 x minus 3/2 on the left, and 5 to the power of 1 on the right. Now 5 to the power of 1, of course, is just 5. And then to solve this for x, we can just use basic algebra. I'm going to multiply both sides by 10. That's going to eliminate my fractions here. So that'll give me 4x minus 15 equals 50, which is 4x equals 65. And then you can solve for x. You end up with 16.25. Question 9, again, pretty similar, but this time we do have a natural log again. So we start off with natural log of 9x plus 10 equals 2. And to eliminate this natural log, to cancel it out, we need to take e to both sides. Remember, e and natural log are inverses, so those go away. So on the left, we have 9x plus 10 equals e squared. Don't forget, e is just a number. I know it looks like a variable, but it's a number. It's 2.71. It's irrational, so it goes on forever. It's a decimal that never ends, but it's just a number. So we're just going to leave this as e squared for now. I'm going to subtract 10 from both sides, and I'm going to divide both sides by 9. This is a number that you can plug into your calculator. Don't try to do this in your head. There is a button on your calculator that just says E. Most calculators, scientific calculators, graphing calculators have that button. And if your calculator just so happens to not have the button, if you're using a very basic calculator, you can usually estimate by just using 2.71 as E. And that will give you your decimal number. You end up with about negative 0.29. The instructions tell you to round to the nearest hundredth, so try to get it as accurate as they ask you to get it, and rounding might be necessary. In question 13, we actually have a more difficult problem than it might appear at first. So we're going to break this down very carefully. We are told at the outset what log base 4 of x is equal to and what log base 2 of y is equal to. So let's keep these two things in mind for a little bit later in the problem. Let's start with log base 2 of x to the 4th, y to the 8th. Since we know something about log of x and we know something about log of y, let's split this up into two separate logarithms. If I do that, since these two are being multiplied within the log, I can split them up using my multiplication property. So that would become log base 2 of x to the fourth plus log base 2 of y to the 8th. Now, I know what log base 2 of y is equal to. I don't know what log base 2 of y to the 8th is equal to, but I know what log base 2 of y is equal to. So what we're going to do now is we're going to use that property, the exponent property, to bring our exponents out to the front of our logs. So the first one becomes 4 log base 2 of x plus 8 log base 2 of y. Now, here is where the other information comes in. We know that log base 2 of y equals 22. So this log base 2 of y can just become 22. We have a bit of an issue though. Log base 4 of x is known to us, but we do not have log base 4 of x. We have log base 2 of x. So right now, at this point in the problem, we're in a bit of a standstill. So what I'm going to do is I'm going to pause here. We will come back to this. But before we do, I'm going to go ahead and work on the second part of the problem. The second part of the problem is log base 2 square root x over y. Now, this one's a little bit tricky because there's a hidden exponent inside of it. Square roots are exponents. They just look a little different. So this is technically x divided by y to the power of 1/2. This is an exponent that we can use our exponent rule to pop out to the front of our logarithm. So we would write this as 1/2 log of x over y. Now, to split this into two different logarithms, because it's division, we have to use our division rule. So we would rewrite this as 1/2. These parentheses are very important. This 1/2 is in front of this entire logarithm. So when we split this logarithm into two pieces, it's going to be inside the parentheses and the 1/2 is still being multiplied to both pieces. So it would look like this. Log of x minus log of y in parentheses. And I just realized I forgot to carry my base. So my base is 2, my base is 2, my base is 2. Just forgot to write that. All right. So again, we have that log base 2 of y. So when we rewrite this, we could write it as 1/2 times log base 2 of x minus, but instead of log base 2 of y, we can put 22 in here. The problem is this log base 2 of x is the same thing that's messing us up in the previous problem. We don't know what log base 2 of x is. We know what log base 4 of x is. So we're going to have to do a little bit of algebra voodoo over here. So we know log base 4 of x is equal to 18. Let's convert that into exponential form. That would be 4 to the 18th power is equal to x. Well, we don't want to have 4 as a base. What we really need is to have 2 as a base. So let's rewrite this 4 as 2 squared. We can do that, right? 4 is just equal to 2 squared. So if I rewrite this as 2 squared to the 18th, then I can see that 2 to the power of 2 to the power of 18 would just be 2 to the 36. Remember, if you have an exponent to an exponent, you multiply your exponents together. So we've successfully turned this from a base of 4 into a base of 2. So if we now convert this back into logarithmic form, we can see that log base 2 of x equals 36. So we have converted our log base 4 into a log base 2. How nice. So that answers our lingering question about the first part of the problem. Log base 2 of x is 36. And we already knew the rest of the problem, so punch this all into your calculator and you end up with 320. And then down at the bottom, Our log base 2 of x, again, is 36, and we already knew everything else. Punch that into your calculator, or do it in your head, you end up with 7. The key to this problem was this trick right here. It can be tough to see that you need to do that. Here is my tip to you. If you end up with a base other than what you're given in your problem, you're going to have to find a way to rewrite your logarithm using a different base. And the easiest way to do that is to convert into exponential form, manipulate it until you get the base that you want, and then convert it back into logarithmic form. In question 14, this is simply a simplification problem. They start us off with 5 natural log of 4 minus 2 natural log of 16, and they want us to convert it into a single logarithm. So all we want to do here is combine these two logs into one. In order to do that, first we have to take care of the numbers that are in the front. So this 5 is going to become an exponent on the 4, and the 2 is going to become an exponent on the 16. So this would rewrite as natural log of 4 to the 5th minus natural log of 16 squared. Now that we just have a single logarithm minus a single logarithm, we can combine these using the division rule. So that would be natural log 4 to the 5th divided by 16 squared. And from here, you're just looking at a numerical problem. You can simplify this. Let's see, 4 to the 5th power. I'm gonna cheat a little bit. 4 to the 5th power would be 4 times 4 times 4 times 4 times 4. And 16 squared would be 16 times 16. Well, 4 times 4 is 16. That would cancel with this 16. And 4 times 4 again is 16, which would cancel with this 16. So, sorry everybody, I just didn't feel like breaking out a calculator for this. So you just end up with 4 over 1, or natural log of 4, as your answer. So they wanted you to write it as natural log of x, where x is 4. There we go. Alright, last problem of the video. We want to solve this for x. Very similar type of logic in this problem. We start with log of 5x plus 4 minus log 2x plus 1 equals 1. And the key to this problem is knowing that if there is no base written, the base is 10. Don't get that confused with natural log. Natural log always has a base of e, but if it actually says log and there is no base written, the base is 10. So that's what you have to keep in mind to solve this problem correctly. So we have we have a log minus a log. We can combine those using our division rule. So that would become log base 10 of 5x plus 4 over 2x plus 1 equals 1. And then to get rid of the log, we have to take 10 to the power of both sides. So on the left, the 10 to the power of log base 10 will cancel. And on the right, we'll just have 10 to the first power, which is 10. Still trying to solve for x, so now it's just a matter of multiplying both sides by 2x plus 1. That will eliminate the denominator on the left. So we have 5x plus 4 equals 20x plus 10. Solve for x by subtracting 5x from both sides and subtracting 10 from both sides, and then divide both sides by 15. We can even simplify that a little bit, which I apparently did not do. You get negative 2/5. And that's a wrap. That encompasses the problem types where you will need to utilize your logarithmic rules. So I hope this video was helpful in getting you started on your homework. More to come.